Hi, this is Dr. Emenacker. In this video, we are going to take a look at computing derivatives of exponentials. In particular, we're going to take a look at how do you compute the derivative of something like e to the x. Okay, well, we're going to go back to what we learned in an earlier video about derivatives, and we're going to use the difference quotient with the limit as h goes to a 0. And in this case, our function f of x is going to be e to the x. When we use the difference quotient, recall that we take our function and first we substitute in x plus h minus, then we compute our function with x substituted in, and that winds up giving us this particular difference quotient. Notice in the numerator we have e to the x plus h. This can be written as this. Now, usually you're used to seeing this the other way around. Usually you're used to seeing things like x squared times x cubed equals x to the 2 plus 3. But in this case, we're going from the side of the equation where the numbers are being added in the exponent to breaking it up into two separate factors. So that's where we get our e to the x times e to the h minus e to the x over h. Notice in the numerator, both terms have a factor of e to the x. We can factor that out, which will give us e to the x times. When we factor out the e to the x in the numerator, we're going to have e to the h right there. And when we factor an e to the x out of this, the only thing that's going to be left is a 1. Well, maybe I'll get that over there. So this is where this term comes from. So we have these two terms now. Okay, at this point, what are we going to do with this? If we factor out the e to the x, we can bring this out front because it doesn't have a variable h in it. So the limit as h goes to the 0 doesn't affect that particular factor. We're left with this limit right here. Well, the catch is we can't plug 0 in. Well, we can. Let's try that. We plug a 0 in there, and we're going to get e to the 0 minus 1 over, plugging in a 0 in the denominator. Now remember, anything raised to the 0 power is 1. So what we really have is 1 minus 1, 0 over 0. Well, that's an indeterminate form, which is a fancy way of saying we have no idea what that means. Okay? So what we're going to wind up doing in this case to evaluate this is we're going to turn to our calculator and we are going to plug in y equals, notice I had to use an x in place of the h because that's the way the calculator likes it, but it's really e to the h minus 1 divided by h. Great. Now remember, I want my variable to approach 0 from both sides. So as I come in toward 0 from the left, look what's happening to these values. It's 0.95, 0.99, 0.999. This is going toward 1. If I come in towards 0 from the right-hand side, for example, 0.1, 0.01, 0.001, I'm getting 1.05, 1.005, 1.0005. This limit is actually approaching a value of 1. So this whole deal here, this limit equals 1 based on what you just saw there in the calculator. Okay, so we have our e to the x times 1, which is our e to the x. And whoa, look at there. What I just got back is what I started with. Notice we started with e to the x as our function that we were going to take the derivative of. And when we take the derivative of it, we get back e to the x. Interesting, but that's what actually happens. The derivative of e to the x is e to the x. So you can jot this down as the derivative of e to the x is e to the x. And that's exactly what we just proved using the difference quotient there. Okay, so with that in mind, let's take a look at a couple of examples and see how this actually works. In this first example, example 1, we have 3 times e to the x. Well, keep in mind, when we have a constant out front, we just bring that constant along, times the derivative of the rest of the function. Well, the derivative of e to the x is e to the x. So for this first example, we just get back what we started with, 3 e to the x, and that's it. In this second example, we have x cubed times e to the x. Now notice here, what's really going on is we have an x cubed times e to the x. Wait a minute, this is a product rule. That's f times g. So using our product rule, we're going to rewrite this as f prime g plus f g prime, and that'll give us our derivative. Okay, so when we take the derivative of f, which is x cubed, its derivative is going to be this 3x squared. Okay, that's fine. Then it says, copy down what g is. Well, that's the e to the x. Plus, because we're using a product rule here, it says copy down what f is. Well, that's not too bad because that's just my x cubed right there. And here comes the new one. We need to take the derivative of g, but g is e to the x. So when you take its derivative, you just get back e to the x, and there you go. There is the final derivative applying the product rule. Let's take a look at a third example. Tell you what, you try this one. Pause the video, work through this as far as you can, and then turn the video back on and we'll go through it together. Okay, so hopefully you actually paused the video and tried this. You can do this one of two ways. You can use the quotient rule here, which looks like that's going to get kind of messy, or I can rewrite this as x to the negative fourth times e to the x, and I'm back to another product rule. Here is my f, here is my g, so here's going to be my f prime g plus f g prime. So it works out pretty easily if you see this not just as a quotient, but hey, I can rewrite this and now I have a product rule. Okay, remember f is x to the negative fourth. So when you take the derivative, the negative 4 is going to come out front as a coefficient. And then when you subtract 1 from the exponent, negative 4 minus 1 is negative 5. Then we just jot down what g is. Well, that's e to the x plus. Now we jot down what f is, x to the negative fourth, and we take the derivative of g. Well, the derivative of e to the x is just e to the x, and ta-da, there you go. We've got it. There is the derivative. As we move into this next one, this is a little strange. Up to this point, we've seen things e to the x, and that's basically all that we've seen. Well, what we have here is a function e to the x applied to another function x squared plus 6x. Wait a minute, when you have a function applied to a function to compute the derivative, you use the chain rule, which is exactly what we're going to do here. Now, if you recall with the chain rule, it's a two-step process. First, you take the derivative of the outside function. Okay, well, the derivative of e to whatever is just going to be back whatever we started with. You get back the same function you started with. So we get back our e to the x squared plus 6x. Got it. Then, according to the chain rule, after you've done that, you now take the derivative of the stuff inside. Well, the derivative of the stuff inside is going to give us 2x plus 6. And basically, that's all there is to it. Doesn't seem horrible. Go ahead and try this one. Pause the computer or the video, give it a shot, and if you get stuck, just fire things back up or take a look at what's written down here. Try this. Okay, so hopefully you actually did pause and try this on your own. One of the things that happens in trying it on your own is at least you've started thinking some about it before we start actually talking about it. One of the things to notice here is this cube root is really x to the fourth minus 3x to the 1/3 power. So we can rewrite it like that. Now, if I have e to that power, when I take the derivative of e, not the exponent, but the e, I get back what I started with. There it is. E raised to the x to the fourth minus 3x to the 1/3 power. Got it. The next part is to take the derivative of this cube root stuff. In other words, we got to take the derivative of this. Well, that's going to be a chain rule in itself. Is it okay to use the chain rule inside of the chain rule? It sure is. So when we take the derivative of this, the first thing we're going to do is the outside part, the exponent. We bring the exponent down as a coefficient. We have a 1/3. We subtract 1 from the exponent. We have a negative 2/3. And we leave what's inside alone. The x to the fourth minus 3x stays just as it is. Now we've done the outside part of the chain rule. What we need to do next is to take the derivative of the inside part of the chain rule. Whoops, the inside part using the chain rule, which is going to be the derivative of this x to the fourth minus 3x. Well, let's see, that's going to give us a 4x cubed minus the derivative of 3x is just 3. And this whole long thing here, everything here all together is the derivative. These things can get to be kind of long. Let's move on and take a look at, not a derivative, but now a second derivative. Well, if you recall, to get to a second derivative, the first thing you need to do is to compute the first derivative. Okay, so to compute the first derivative, I'm going to look at this function right there, and it's e applied to the 6x squared. This is going to be a chain rule, but that's fine. With a chain rule, the first thing you do is you take the derivative of e, which is pretty straightforward. It's just going to give us back e to the 6x squared times. Now we take the derivative of what's in the exponent. In other words, we take the derivative of the 6x squared. That derivative is going to give us a 12x. You can leave it in that form, but typically it's more appropriate to write this as 12x times e to the 6x squared. This will help us as we move into computing the second derivative. Okay, so let's go after the second derivative now. Well, let's look at our original function. Our original function in this case is the first derivative. The 12x is going to be f. The e to the 6x squared is going to be g. Okay, so when we do the derivative, we want to use the product rule. So we're going to do the derivative of this. And the derivative of the 12x is going to be 12. Now, with the product rule, it's f prime times g. Well, that just means we copy down this e to the 6x squared. Then the second part of the product rule says we're going to do f times g prime. Well, f just says to copy down. Better put my plus sign in here. Copy down this 12x. Then for the g prime, that's a chain rule. We're going to have e to the 6x squared. Okay, remember we're first just taking the derivative of e, which just gives us back what we started with, put this 2 up here so it really is obvious it's in the exponent. Then we take the derivative of the exponent. Well, the derivative of 6x squared is 12x. Well, that's kind of a mess that way. This can be rewritten as a 12e to the 6x squared plus. Now notice we have a 12x and a 12x, which gives us 12 times 12. And 12 times 12 is going to be 144. And we have x times x, which is going to be x squared, e to the 6x squared. You can stop there if you want, okay? If you wish, you can factor out what both have in common. Now notice they both have a 12, and they both have an e to the 6x squared. So I could factor out a 12 e to the 6x squared. And what I'll be left with in this first term here, we factored out everything, so we're just left with a 1 plus. In the second term, when we divide 144 by 12, we're going to get 12, and we're still left with this x squared like that. And there's the derivative. Factoring out the e to the whatever is going to be an important maneuver. The reason is, if you'll recall, we've already looked at scenarios where we want to find where is the derivative or the second derivative 0. Well, if you look at e to the x, a graph of e to the x over here toward the right goes like that. It never hits the x-axis, so it's never 0. If you factor out the e to the whatever it is, in this case 6x squared, you're left with this second factor that you can then set equal to 0 and see if that part has a solution. So when we're taking our derivatives and then needing to set them equal to 0, you're going to want to factor out this e to the whatever power of x it is to allow you to have two separate factors and set each individual factor equal to 0. The e to the 6x squared in this case, never 0. Actually, the 1 plus 12x squared is never 0 either. It winds up being a complex number. So in this case, in the real numbers, there's no solution. And that's a perfectly legal answer. Okay, let's take a look at this one. It says Andy invests $15,000 into an account that earns 8.5% continuously compounded. Now, because it is continuous compounding, we're going to use this equation PERT. P sub 0 is the amount you start with, 15,000. E, the interest rate is 8.5%, so it's going to be 0.85 when you convert it from a percentage back to a decimal. So there's the equation we're actually going to be working with. Okay, so now it's time to get out the calculator again. And what we need to do here is find some place we can put the calculator. There we go. We want to compute A at 3. So I'm going to fire this up and I'm going to quit. Now, what I have here is 15,000 times E raised to the 0.085. Now, on our equation, it says t, but in the calculator, it wants to use the value x. However, we don't want to put x in. In this case, we want to put times 3, because remember, we're trying to evaluate this at a of 3. Okay, so I go ahead and I crunch that out, and this is $19,356.92. So let's see if I can remember that. $19,356, and I forget how many cents that was, but we can get it back pretty easily. There it is, 92 cents. Okay, so it says compute it. There we go. Interpret it. Yeah, we need to figure out what does this number mean. What this means is that in 3 years, see the 3 here? In 3 years, the total amount in the account will be $19,356.92. So there is the value for A of 3. We're then asked to compute A prime at 3. Okay. So A prime of t, I'll do that first, is going to be 15,000 because that's just a coefficient. It comes along. Now I need to take the derivative of e to the point 0.085t. This is going to be a chain rule again. Take the derivative of the e, or the outside part, and we get back whatever it was we started with. It's going to be 0.085t. After we've done that, we now take the derivative of the exponent. Well, that's going to be 0.085. We can clean this up some. By cleaning it up, I mean I'm going to take the 15,000. I'm just going to use my handheld calculator here. 15,000 times 0.085 equals, which means we're going to have 1,275 e raised to the 0.085 times 3. Okay, so if I do the 1275 times e to the 0.085 times 3, this gives us a value of $1,645.34. Now be careful. This does not mean that the amount of money in the account is going to be $1,600. We just saw in the previous one, the amount of money in the account better be over 19,000. What this says, okay, is, I'm going to type it out this time. As we go from year 3 to year 4, the amount in the account will increase by $1,645.34. Remember, the derivative is a slope. This slope is that number 1645 over 1. So it's $1,645 per 1 year. Remember, as a slope, you're going to use the function's value divided by whatever the value of t is. Well, t is in terms of years. Okay, so as we go from year 3 to year 4, the amount in the account will increase by $1,645.34. Okay, so let's take a look at this one last problem here in this section. We're told that a new worker is hired for a production line, and the number of units produced per day increases as the worker gains experience. That makes sense. The first day, they're probably not going to be as productive as they are on the second day, etc. And it says the number of units produced per day by a newly hired worker, okay, is given by this equation. N of t equals 115 minus 80 e to the negative 0.2 t. Whew. Okay, so we're going to compute and interpret n of 3. Well, n of 3 is going to be 115 minus 80 e to the negative 0.2 times 3. Okay, so I can plug that into my calculator, and I got this 115 minus 80 times e to the negative 0.2 times 3, and boom. This works out to be 71.095. Now remember, they're making some product. 0.095 of a unit makes no sense. So what this says is that by the third day, or actually on the third day, the worker should produce or make 71 units, whatever these things are. Now, one of the things to be mindful of is suppose this had worked out to be 78.64. At the end of the day, there are really only 78 saleable units made. Okay, so you don't just round this up to 79 because there are not 79 units that person has made. There are really only 78 and there's part of one. Okay, so when we're working with physical things, you need to be careful to make sure that you're handling the decimals in an appropriate fashion. Okay, now let's take a look at this second part. We're going to compute n prime of t. Well, I'm looking up here at the top of the screen. The derivative of 115 is 0 minus, I have this 80. Now I'm going to have the derivative of e to the negative 0.2t. But remember, this is going to be a chain rule. So we're going to take the derivative of the outside first. Well, that's the derivative of e. And whenever you take the derivative of e, you get back whatever it was you started with. So we have e to the negative 0.2t. Then, as with all good chain rules, you now take the derivative of the inside part. Well, the derivative of the inside is just this exponent, the negative 0.2t, and the derivative of that is going to be a negative 0.2. This will clean up some because we can take the negative 80 times the negative 0.2. Okay, and if we take that, we should get 16, and it'll be positive. E to the negative 0.2t. Okay, what we're asked to actually compute here is the derivative at 3. So this is going to be 16 e to the negative 0.2 times 3. And if I plug that into my calculator, we have 16 times e to the negative 0.6, because 0.2 times 3 is negative 0.6. And this is going to be equal to 8.78. Now, remember, we've just done a derivative. A derivative is a slope. So this could really be written as over 1. Now, let's think about what the units are. Okay, if we're thinking about a slope, it's the change in y over the change in x. The y is the value that comes out. And the value that comes out, as we saw in the first one, is in terms of units, product, whatever it is. So the label or the unit on the change in y is going to be units, products, whatever you want to call it, per, and then t is in days. What this 8.78 means is, let's see, it might be quicker just to type this. What this is telling us is, okay, from day 3 to day 4, the worker's productivity will increase by 8.78 units. Or what this really means is on the 4th day, the worker should complete an additional 8 units. Okay? Remember, the 0.78 is not an entire saleable unit. There are, the worker will make whatever they did on the third day. Okay, so on the fourth day they'll come in, they'll be able to make as many as they did on the third day. And then because they're getting the hang of it a little better, they'll make 8 more units. Not 8.78, but there will be 8 more saleable units on that day. Hey, I hope this is helpful to you. If some of this seems a little fast, remember you can always pause and back up the video at any point you need to. Take care.